Namaste and welcome back to my channel Qubit Educational Services. In this video we are going to solve 2 marks questions from GATE XE 2007. We are going to start with question number 7. We first completed all 1 mark questions in our previous video. The 7th question is on linear algebra. It says let Ax equal to B be a system of m linear equations in n unknowns with m less than n, and B is not a null matrix or null vector. Then the system has n minus m solutions, either 0 or infinitely many solutions, exactly one solution or n solutions. Now we can easily eliminate options A and D. Okay, we can easily eliminate options A and D because we know that any system of linear equations will either have a unique solution, or it will have no solution at all, or it will have infinitely many solutions. Correct? And in n minus m or n, these refer to, or these may refer to natural numbers like 2, 3, 4 and so on, and they are finite, so we cannot have A and D, right? So it is either B or C. So let's now figure that out. It's given that our system contains m linear equations and n unknowns, and this condition that the number of equations is less than the number of unknowns is important, because if we write Ax equal to B in the matrix form, okay, then we know that the coefficient matrix is going to have as many rows as the number of equations. So if it has m linear equations, then it will have m rows, and then because it has n unknowns, it is going to have n columns. And similarly the orders of X and B follow. Now what is the condition for existence of solutions? Okay, we'll talk about that now. We know that rank of any matrix, okay, rank of any matrix is less than or equal to the smaller of the number of rows and the number of columns. Correct? We know that. In this case, they're saying that m is less than n, so A has less number of rows than columns. Correct? So whatever the rank of A be, it has to be less than or equal to m. Okay, the rank of coefficient matrix has to be less than or equal to m, which is the number of equations in the system. Now what does this imply? This implication, this conclusion is important. You should be able to draw the correct conclusion here. Okay, now whether the system is consistent or possesses solutions is decided by the equality of the ranks of the coefficient matrix and the augmented matrix AB, isn't it? Now we are free to assign any value to the rank of the augmented matrix AB, which then means if the ranks were equal or are equal, then it will have infinitely many solutions. Okay, because it anyways is less than the number of unknowns. Okay, it's less than the number of unknowns. But if the ranks are unequal, then it will have no solution at all. Correct? So both the possibilities are open here. If you want, if you play a little bit with these things, then you can even come up with an example one each for infinitely many solutions with m less than n, and even no solution case with all the requirements being met in the problem. So the correct option to question 7 is B. Question 8, again a linear algebra problem, but this time it is based on eigenvalues and eigenvectors. Let R be an n by n non-singular matrix. Let P and Q be two n by n matrices such that Q is equal to R inverse P into R. If X is an eigenvector of P corresponding to a non-zero eigenvalue lambda of P, then Rx is an eigenvector of Q corresponding to the eigenvalue lambda of Q, Rx eigenvector of Q corresponding to eigenvalue 1 over lambda, R inverse X eigenvector corresponding to eigenvalue 1 over lambda, or R inverse X an eigenvector of Q corresponding to the eigenvalue lambda of Q. This is a problem which not only requires you to know the main eigenvalue equation or eigenvector equation, but it also requires you to know the associative property of matrix multiplication. So we are going to start by writing down the given equation Q is equal to R inverse P R. Correct. Now, because they have given us that X is an eigenvector of P corresponding to the eigenvalue lambda, we must write this equation as well. Px is equal to lambda x. That's the main equation. We will continue simplifying Q or this equation, the first one, as long as we get Px on one side. So we can replace Px by lambda x. Then we can think about the eigenvector and eigenvalue of Q. So I'm going to simplify this. The first step is I'm going to pre-multiply both the sides by R. If I pre-multiply both the sides by R, I will get RQ here. RQ equal to R into R inverse identity matrix, I will not write it, is equal to PR. Now I will post multiply both the sides by R inverse. RQ R inverse is equal to P R R inverse, associative property of matrix multiplication, club R and R inverse together, you will get identity matrix P into I is P. And now we will bring in this part. So we have P here, so we will say post multiply both the sides by X. Therefore RQ R inverse X is equal to Px. But what is Px equal to? Px is equal to lambda x. Correct. Now we are not interested in eigenvector or eigenvectors of RQ. We are interested in eigenvector of Q. So we will now pre-multiply both the equations by both the sides of this equation by R inverse. So this R will go, the first R. So we will get Q into R inverse into X equal to, I will not write Px now, I will write lambda x. We have pre-multiplied both the sides by R inverse. So it is R inverse into lambda x. Okay, therefore Q into R inverse of X is equal to lambda into R inverse of X. Again we are using the associative property. Even if it is a scalar lambda and a vector or a matrix R inverse, we can write the scalar anywhere. Either we can write it as a multiple of the second matrix or the first matrix. Now this equation is important. This equation is directly going to tell us the answer. If you compare this with Px equal to lambda x, we are post multiplying Q by R inverse of X, and we are getting the same result if we multiply R inverse of X by a scalar lambda. What does that mean? That means lambda must be the eigenvalue of Q corresponding to the eigenvector or an eigenvector R inverse into X. So it is option D. Lambda is an is the eigenvalue, and an eigenvector corresponding to that is R inverse of X. Simple problem, question 8, option D. Next is question 9, based on the Cayley-Hamilton theorem. Let M be a 2 by 2 matrix with eigenvalues 1 and 2, then M inverse is, and we have 4 options. The moment you see the appearance of the matrix itself and the identity matrix, you have to guess that it has to be a problem on Cayley-Hamilton theorem, because Cayley-Hamilton theorem is one of the techniques to evaluate the inverse of a matrix. Now it is a 2 by 2 matrix. So if you don't know, there is a shortcut to find the characteristic equation of a 2 by 2 matrix. In usual notations, it is lambda squared minus the trace of the matrix into lambda plus the determinant of the matrix equal to 0. So if you solve this equation, then you will get the eigenvalues. Eigenvalues are the roots of this equation. This equation is valid only for a 2 by 2 matrix. Now, the properties of eigenvalues are the trace is the sum of the eigenvalues. So in this case it is 3, and the determinant is the product. So in this case the product is 2. So the characteristic equation is lambda squared minus 3 lambda plus 2 equal to 0. This is the characteristic equation. Now if you remember the Cayley-Hamilton theorem, it says every matrix satisfies its own characteristic equation. So in this case lambda will get replaced by m, and in the last term it's 1 that will get replaced by the identity matrix. Therefore we will get m squared minus 3m plus 2i equal to 0. Now okay, you can't say 0 now, although we should write 0. That's a null matrix. In this case it's a number because it's a polynomial equation whose roots are real or complex numbers. But here it's a matrix, so right side cannot be 0, it has to be a 2 by 2 null matrix. Next, let's multiply, pre or post multiply both the sides by m inverse. So m squared will be m will be I, and I will be m inverse. Null matrix, so that will remain as it is. Now rearrange the terms. First of all, send m and 3i to the other side. Negative 3i, so positive 3i, positive m, so negative m. And on this side you still have 2m inverse, so m inverse will be 3i minus m divided by 2. That is option C. It's a fairly simple question. Question 10. The number of n by n matrices that are simultaneously Hermitian, unitary and diagonal is 2 raised to n, n squared, 2n and 2. To solve this problem, we will first write down the definitions of Hermitian, unitary and diagonal matrices. A unitary matrix has this characteristic that its inverse is equal to its conjugate transpose. So you not only take the transpose, you also take the complex conjugate of every entry. And when inverse is equal to its conjugate transpose, you call those matrices as unitary matrices, and their characteristic is that their eigenvalues are unimodular. Remember, these eigenvalues can be complex numbers, but they should lie on the unit circle in the Argand plane mod z equal to 1. So unimodular is the property of unitary matrices, which is useful here. Okay, it's required here. Correct? So for unitary, we have got the condition that all the eigenvalues should lie on the unit circle. Okay. What is Hermitian matrix? Hermitian matrix is a matrix where the matrix is equal to its conjugate transpose. It's similar to symmetric matrices. It is the complex analog of symmetric matrices. A is equal to its conjugate transpose. And one of the characteristics of Hermitian matrices is that they have real eigenvalues. Okay, they have real eigenvalues. Now the thing about Hermitian matrices is that if we want a matrix to be both Hermitian and unitary, then mod z equal to 1 is true for unitary matrices, and these have real eigenvalues. So you can say that if we impose both the conditions now, then the eigenvalues can be just plus 1 or minus 1, because though they are the only two real numbers which are unimodular, their modulus is 1. Now what is a diagonal matrix? That is going to answer the question now. Diagonal matrices are such that, well, all the non-diagonal entries are 0 and the eigenvalues themselves are along the diagonals. So which then confirms now that we have two options to fill the entries of the diagonal element, diagonal matrix. Correct? Which two options? Negative 1 and positive 1. And what is the size of the matrix? The size of the matrix is n by n. So we have n options. Okay, rather n places to be filled, either by 1 or negative 1. And if we apply now the multiplication principle, okay, it will be 2 raised to n. How? Here a11 either negative 1 or positive 1, so 2. Second row, second column, again negative 1 or positive 1, so 2. Third, so on till the nth. So how many powers of 2? You should have n powers, and that will tell us that the number of such matrices which are simultaneously Hermitian, unitary and diagonal is 2 raised to n. That is option A. So this whole problem is simple, but it not only requires you to know the definitions of unitary and Hermitian matrices, but also the characteristics of their eigenvalues. For example, unitary, as the name suggests, have their eigenvalues unimodular. Hermitian matrices have their eigenvalues real, and for diagonal you already know the things. Question number 11. Let M be the matrix 1BA 02C 001 where A, B, C are real numbers. Then M is diagonalizable for all values of A, B, C only when BC is not equal to A, only when B plus C is equal to A, only when BC is equal to A. First thing that you should note about matrix M is that it is an upper triangular matrix. M is upper triangular. Now for any upper triangular matrix, the eigenvalues are its diagonal elements. So its eigenvalues are 1, 2 and 1. When is a matrix diagonalizable? A matrix is diagonalizable if its eigenvectors corresponding to its eigenvalues, identical or distinct, should be linearly independent. Now we already know that if a matrix has distinct eigenvalues, then it is always diagonalizable, because eigenvectors corresponding to distinct eigenvalues, they are always linearly independent. But for the matrix M, because this element is equal to this element, we need to investigate this situation further, and that is what the problem asks us to do. When can M be diagonalizable, although it has two eigenvalues which are equal? Now to proceed, we will first write down the equation that we use to find the eigenvectors or eigenvectors. That is M minus lambda I into the eigenvector or an eigenvector x equal to null matrix. So if I let lambda to be 1, and I will this time be identity matrix of order 3, which equation will I get? I'll get this 0, 1, 0. We have to subtract 1 from all the diagonal elements, and everything else will remain undisturbed. So BAC here, 0, 0, 0 here. The matrix X, which is our eigenvector, equal to null matrix. Now how many eigenvectors are we expecting? How many linearly independent eigenvectors are we expecting? 2, because we want the matrix to be diagonalizable. When is that possible? That is possible when the rank of M minus lambda I is 1. We already know that it is 2, or rather less than or equal to 2, because of the third row being 0. So the rank of this matrix M minus lambda I is either 2 or 1, but the moment it becomes 2, the eigenvectors corresponding to 1 become linearly dependent, all of them. We don't want that, because that would make M non-diagonalizable. We want it to be diagonalizable, so rank should be equal to 1 for diagonalizability. Hope that's the right word, diagonalizability. Okay. So when is that possible? That is possible when the determinant BA1C is equal to 0. Correct? The second row should be dependent on the first row. We can perform the elementary transformations to make zeros here instead of this one and this C, and without disturbing the first 0 in the second row. That is possible when this is 0, or BC minus A equal to 0, or when BC is equal to A. That is option D. Question 12. The maximum value of the function 2x plus 3y plus 4z on the ellipsoid 2x squared plus 3y squared plus 4z squared equal to 1 is 2, 3, 6 and 9. This is a problem on constrained optimization. This is a problem on constrained optimization. In the 12th standard, you must have learnt about linear programming problems, correct? So that is another category of constrained optimization, because there you have constraints in terms of inequalities. In the subject called operations research, if you have studied it, even there we use a constraint optimization. It is a generalization of the linear programming problems, generalized method called simplex method. Here we use constraint optimization using partial derivatives. Specifically, we are going to apply the Lagrange's method of undetermined multipliers. So we shall first write down the functions that we have. 2x plus 3y plus 4z, that is the function that we want to maximize. And what is the constraint? The constraint is that our point x comma y comma z, or its coordinates, should satisfy this equation, or the point should be on the ellipsoid surface. So we will not write down the right side equal to 1. Okay, we'll just write down the left side, 2x squared plus 3y squared plus 4z squared. The Lagrange's method tells us that in such a direction where the optimum value is obtained or is found, the maximum or the minimum, the gradient of the function to be maximized, that is del f, should be collinear with the gradient of the constraint function, or its left side at least. So it will be delta f is equal to, or del f is equal to lambda into del g. This is nabla or del, which we use for representing the operation of gradient finding. Correct? Okay, so now we will apply the definition of gradient, which is a partial derivative of the function with respect to x I cap and plus so on for j cap and k cap. So that's very simple, because the partial derivative of f with respect to x is 2, with respect to y is 3, with respect to z is 4. Now we will do the same thing for g. Partial derivative of g with respect to x is 4x plus 0 plus 0, so that is 4x. And similarly, if we find the partial derivatives of the left side with respect to y and z, then we'll get 6y and 8z. Now we have to solve this equation by comparing the coefficients. What do we get? We get 2 equal to 4 lambda x, 3 is equal to 6 lambda y, and 4 is equal to 8 lambda z. Now we want to make use of the equation of the constraint, okay, so that we can find the value of lambda. So we will get x, y and z in terms of lambda. We will get x, y, z in terms of lambda. X will be 2 by 4 lambda, or 1 over 2 lambda. Similarly, y and z also turn out to be 1 over 2 lambda. As you can see, 3 is half of 6 and 4 is half of 8. Now let us substitute these in equation of ellipsoid. In the equation of ellipsoid. If we do that, because that is the constraint, isn't it? After all, this is constraint optimization. We want the point to be always on this ellipsoid. If you do that, 2x squared plus 3y squared plus 4z squared equal to 1. If you substitute everything, then you will get 2 plus 3 plus 4, that is 9. 4 plus 3, 7, 7 plus 2, 9. Square of 1 upon 2 lambda is 1 over 4 lambda squared equal to 1. That will give you 2 values of lambda. That will give you 2 values of lambda. Now which one of them will we choose? We want to find the maximum value, right? Of which function? We want to find the maximum value of the function 2x plus 3y plus 4z. So we would like all of them to be positive and not negative because of the maximum value, right? And therefore we will pick lambda to be positive 3 by 2 for maximum value, and x, y and z, all of them are equal to 1 over 2 lambda. 1 over 2 lambda means 1 upon 2 into 3 by 2, because we have rejected negative 3 by 2 for obvious reasons. so 2 into 3 by 2, that's 1 upon 2 lambda, that will be 1 upon 3, and 2x plus 3y plus 4z, if you substitute x, y, z to be 1 upon 3, it will be 9 into 1 upon 3 or 3. So the correct option is B. So the correct option is B. Question number 13. Let f be a function defined from the set of real numbers to the set of real numbers, and suppose it is twice differentiable real value. The additional property that the function f possesses is f of 1 over n is always 1 for all the natural values of n. So when n is 1, n is 2, n is 3, so on, it is 1. Then derivative of the function at 0 equal to 1, lies between 0 and 1, or is positive. To solve this problem, we are going to build a function, or take a function, a simple function, which will be twice differentiable real valued, and it will also possess this characteristic that f of 1 over n is 1. The function that I am going to consider is constant function, f of x equal to 1. Is it twice differentiable? Yes, it's a constant function, so it can be differentiated infinitely many times. Is it real valued? Yes, it is real valued. Now, does this satisfy this requirement, f of 1 over n is 1? Yes, in fact it is equal to 1 for all values of x, no matter what you put. So this condition is also satisfied there. Now it's simple, right? You just differentiate this, f dash of x will be 0, and the good news about why this function will work is that all the options are exclusive. So it can either be 0 or 1, or in between 0 to 1, or greater than. So here we have got f dash of x equal to 0 for our function, which meets all the requirements posed in the problem. So if I substitute x equal to 0, that will give me f dash of 0 equal to 0. That is option A. So you may employ this approach in other multiple choice questions or numerical answer type questions if the problem has been designed that way. If the result is in general true, because you know that only one option is going to be right. So if the result is true for a general case, it must be true for a simple or simpler case, and that is what we have done here. Question 13, option A. Let's go to question 14th. Question 14th, let f of x be the function defined using the definite integration, integral of sine of root t with respect to t from 0 to x squared for x greater than or equal to 0, then the derivative of f at pi by 2 is equal to 0, pi, 1, pi by 2. This is a standard problem on Leibniz rule. We have to find the derivative. So let's first write down the expression for the Leibniz rule. It tells us if we want to differentiate the function, then we would first be differentiating the integrand partially with respect to x. Now we call x a parameter. So it's partial derivative of sine of root t with respect to x dt plus. Now we will be placing the upper limit for t. So it will be sine of root of x squared. So I can write it as x because x is greater than or equal to 0 into derivative of x squared minus sine of 0, that's the lower limit, and we need not write the derivative here because it is also 0 and also sine 0 is 0. So this is a Leibniz rule. If you open any standard calculus textbook, you'll find this. Okay, fine. So will the first term be 0? Yes, because there is no x in this integrand, so the partial derivative will be 0. So this will be 0. What about this? It's already 0. So derivative of f with respect to x is sine of x into 2x. Sine of x into 2x. At pi by 2, we get sine pi by 2 into 2 into pi by 2. Sin pi by 2, 1. 2 gets cancelled. 1 into pi. Option B. Fairly straightforward problem.